Dun dun dun! Describing heat changes. There are two types of heat changes. Endothermic and exothermic. They're very easy to get confused. So hopefully you won't get confused. Okay, so first we need to go over that wonderful term again. Enthalpy, which is delta H to the chemist, which is Q to the physicist. This is the amount of heat lost or gained by the system during the process, such as a reaction or a phase change at constant pressure. Okay, now, there are two types of reactions, okay, that involve heat changes here. There's the infamous exothermic, and then there's the wonderful endothermic. Exothermic is when heat is lost by the process, indicated by a negative delta H. Negative delta H. Which means that work is done on the surroundings. Meaning that the surroundings get usually warmer. Okay. Surroundings get hotter. Okay. As heat is given off by the system. You have to be taking in mind your frame of reference here. You have to, when I tell you what the work is doing, I always have to tell you if it's on the surroundings or on the system. Okay? Because it's two different things. Okay? So, in an exothermic process, heat is transferred from the systems into the surroundings. Heat is lost from the system, so the temperature of the surroundings increases. Okay. The system releases energy as bonds or intermolecular forces are formed. Then we got endothermic here, which has a positive delta H. Positive delta H. When heat is gained by the process. So what this is work is done on the system. That makes sense because you're adding heat into the system in exothermic and in exothermic. In endothermic, heat is added to the system. In exothermic, heat is lost from the system. Okay? This means the surroundings get cooler and the container will feel cold. Okay. So here, heat is transferred from the surroundings into the system. Since heat is lost from the surrounding, the temperature of the surroundings decreases. And the system uses the energy to take in to break bonds or to increase the kinetic energy of the molecules. Okay, hopefully you can see all that. Okay, give you a second to ponder that. Ponder, ponder, ponder. Okay, this, oh my goodness, this table. This table is, as I would say in my bad Spanish accent, muy importante. Muy importante. Do 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 do. Muy importante. Muy importante. Okay. So, in an exothermic reaction. So exothermic's over here. I have to go slow because I always have to write this stuff down just to keep myself straight here. So let's start off with exothermic here. Okay, so energy is released in exothermic. The temperature of the surroundings is increased. Delta H would be negative. Okay. And then notice that the heat in an exothermic process, heat is on the product's side. As it is exiting the system. Okay, so it is on the product side. Okay, now on this wonderful exothermic diagram here, this first part is the energy needed to break bonds. Okay. So it is required to add energy to break bonds. That says break bonds. This is to form bonds. So energy is released when bonds are formed. When the reactants, delta H of the reactants, is greater than delta H of the products, why do I want to put delta? That is one way we can tell it is exothermic. You usually see me draw an exothermic diagram. Let me go up here and draw an exothermic diagram. I over-exaggerate it, but it looks like that. That is an exothermic energy diagram because the products are lower. Okay, let's discuss endothermic now. Endothermic. Dun, dun, dun. Here is where energy is required. The temperature of the surroundings is decreased. Delta H is positive. And then heat, notice heat's right here, heat is on the reactant's side. Okay. Again, you need energy to break bonds. And then you lose energy to form bonds. That always happens. Okay. So here, if delta H, no, not delta H, if H of reactants is less than H of products, then it is endothermic. Okay. And here is my over-exaggerated diagram for this one. Endothermics, they usually look like that when you look at an energy diagram. Notice that the products here, because the products is where you end and the reactants is where you start, the products are higher than the reactants. Okay, let's go to the next page. Okay, time to go over some definitions here. The minimum amount of energy that must be to overcome the reactants to convert into products, this minimum amount of energy is called the activation energy. Okay. The energy barrier is often referred to as an energy hill. That's what I refer to it as too. The reactants must collide with enough energy to overcome the hill. Yes, according to collision theory. Because everybody loves collision theory, right? Guess what? It's a theory about collisions and making reactions happen. You have to have three things for a reaction to happen. Number one, the atoms must collide. If they do not collide with each other, then they're not going to react. They must have sufficient energy. Okay? In other words, they have to get over this energy hill right here. So if it only gets up to here, it goes back down to reactants. But once it gets up to here, woo, we go over the hill and we get back down to products. And they must collide with the correct orientation. In other words, you have to put the puzzle pieces together right. Okay. So, yeah. Okay. So the energy barrier is referred to as hill. At the top of the energy barrier, there's a transition state called the activated complex. Okay. This is what we call a transition state. Is that words in here? Oh, by Jove, they are. Transition state. Okay. At this transition state, this is where bonds are broken and formed. Okay. Okay, if you increase the temperature, they have more kinetic energy, there's going to be more collisions, so the reaction will happen faster. Okay. Okay. The difference in energy between the activated complex and the reactants is the activation energy, okay, which is the activated complex. What do I want to do? Energy of the activation complex minus energy of the reactants. I should probably use delta H, but whatever. I used energy this time. Okay, and then the difference between products and reactants, this is what we call the heat of reaction, or the enthalpy of reaction. Delta H is equal to products minus reactants. And activation energy is equal to activation energy minus reactants. Okay, so if I'm looking at this energy diagram over here, okay, this is the reactants, is where we start. This is the products, that is where we finish. Okay, at the top here, because I think of a story, and they always tell me in English class that the story always comes to a climax at some time. So the complex, to me, is at the top, just like the climax of a story is the most exciting part of the story or whatever. Okay. The delta H is the distance from products to reactants. The activation energy is the distance from the activated complex to the reactants. Let's look at some examples. Okay, so we are going to label the following. Reactants is where we start. Products is where we finish. Reactants is where we start. Products is where we finish. The activated complex is the top of our energy hill. Okay. Delta H for the forward reaction. Okay. So delta H for the forward reaction is from here to there. So this is delta H forward. And then this would be delta H backwards. Okay. Whoops. Reverse. I want to put reverse there. Because if you're talking about the reverse reaction, the products become the reactants and the reactants become the products, so then it's the reverse. So if the forward is exothermic like it is here, the backwards has to be endothermic. Okay. Okay, likewise here, gotta go from products to reactants, that is delta H forward. Delta H backwards is from reactants to products. Okay. The activation energy of the forward reaction here, let's change colors here. So the activation energy from the forward reaction would be from here to there. The activation energy of the reverse reaction would be from there to there. Okay. The activation energy for the forward reaction here would be from here to there. And the activation energy for the reverse would be from there to there. Okay. Okay, I think that probably confused you more, but now I'll try to correct it in a second here, because I got an idea going through my head. Okay, so this one is exothermic for delta H forward. So what is the delta H value? So you do products minus reactants. So this is 20 minus 40, which is negative 20 kilojoules. Oh, look, delta H is negative. Yeah, delta H is negative. Exothermic, dun, 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 dun. Exothermic, dun, 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 dun. Delta H negative, exothermic. Okay. What is the activation energy value? So this is 100 minus 40, which would be 60 kilojoules. That would be the activation energy. Okay, and this one here, let's do the delta H value first. So now I'm going to do 20, because it's still products minus reactants, minus 10, which is positive 10 kilojoules. Endothermic. Endothermic, delta H positive. Endothermic, delta H positive. Okay. And then the activation energy here is 50 minus 10, which would be 40 kilojoules. Okay. Sketch out the following potential energy diagram. Oh boy. Here we go. So we need a diagram. Dun, 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 dun. Okay. Progress of the reaction. Potential energy in kilojoules. Okay, so reactants, 50. 75. Products. That's going to be the end. 100, 125, 150. That's going to be the activated complex. Okay, so we draw a diagram. Okay, there's an energy diagram. Okay, what is the activation energy for the forward reaction? That would be the distance from the activated complex to the reactants. Okay. So that would be 150 minus 50, which would be 100 kilojoules. Okay, now we're doing the reverse reaction here, so now we're going from the products. Okay, so this was forward. So for the reverse reaction, we're going to go from here down to there. Which means this reaction must be in equilibrium. So this is 150 minus 75 kilojoules. The activation energy is always a positive value. Okay, what is the enthalpy of the reaction? So for the enthalpy, for the delta H, you got to go from products to reactants. So this is 75 minus 50, 25 kilojoules, positive delta H, endothermic, positive delta H. Okay, enough of that. The legend is out. You guys are total champions for putting up with us for 20 minutes.